Hi, Assalamualaikum. My name is Nurul. My metric number is S63726, and today I will be presenting about ocean ion fertilization.
So we will start with the first one. Ion fertilization is the removal of atmospheric carbon dioxide by nutrient addition, in this case iron, to promote phytoplankton growth and carbon export to the deep ocean. Iron is essential micronutrient for the growth of primary producer. In the subarctic North Pacific, equatorial Pacific, and the Southern Ocean, which are well known as high nutrient low chlorophyll (HNLC) regions. Phytoplankton cannot completely utilize the available macronutrients for photosynthesis due to the lack of iron. Next, the atmospheric carbon dioxide level at the last glacial maximum 20,000 years ago was substantially lower than during pre-industrial times, around 180 ppm to 280 ppm, according to analysis of trapped air bubbles in Arctic, Antarctic ice cores. Many theories have been put up in the last 25 years to explain the decreased atmospheric carbon dioxide during the LGM. Next, in 1990, John Martin proposed that during a LGM, higher dust inputs relieve iron constraints and significantly improve the biological pump in HNLC regions. Dust inputs are recognized as a primary natural iron source for ocean fertilization. Since Martin's hypothesis was initially published, there has been a lot of interest in ocean iron fertilization because it only requires a small amount of iron to drive potent phytoplankton resources. The carbon to iron ratios are around 100,000 to 1. As a result, much of the research has focused on adding iron artificially into these zones in order to improve carbon fixation and subsequent export via the biological pump. So the main objective of OIF is to promote phytoplankton growth in order to capture and store atmospheric carbon dioxide in the ocean for a very long time. So, for the next question, these are the area of fertilization and why they are chosen. In equatorial Pacific, these areas are high temperatures and light intensity, so this would encourage rapid phytoplankton development. And in the Southern Ocean, the iron supply is very significant, boosted by the dust inflows and even by icebergs. The availability of silicate plays a role in regulating the primary productivity in this region. And in subarctic North Pacific, is they exhibit a considerable longitude gradient in aeolian dust deposition, with high deposition in the west and the east compared to equatorial Pacific and Southern Ocean. And then lastly, subtropical North Atlantic has high phosphorus and iron, which are typically co-limiting factors for primary productivity in LNLC environments, which are predominantly populated by nitrogen fixers. On to the importance of ocean iron fertilization, which is the iron climate relationship. There is an urgent need to cut global greenhouse gas because the beginning of the Industrial Revolution has generated a rapid increase in atmospheric carbon dioxide, which caused global warming, ocean acidification. There are different theories. The first one, decreasing the atmospheric carbon dioxide by enhancing the biological uptake and directly capturing it. And the second one is controlling solar radiation by injecting artificial aerosols into the atmosphere to increase cloud formation and cloud brightening to raise albedo. In order to promote the intake of macronutrients for phytoplankton growth, iron functions as a very important micronutrient. This holds carbon for a very long period and can restore the climate to its pre-industrial state. These are the ocean iron experiment and limitation. Equatorial Pacific have two experiment, and some of the limitations are insufficient experimental periods to observe full phases of the biogeochemical processes, and they only happen to do a single iron addition. And then in iron X2, no export flux measurements in the deep ocean. In the Southern Ocean, there were 7 experiments done. Three of the experiment contains insufficient experimental durations. And for suffix N, there are physical mixing that draws silicate dissolved into fertilized region. And for sage, the fifth experiment, high dilution rate by small patch sizes. And the third one, the subarctic North Pacific, you can see that series and seeds 2 have no limitation, whereas seeds 1 there are the few limitations, which is single iron addition and insufficient experimental duration. These two are seen quite a lot in the other experiments, especially the duration, which most of the experiments are doesn't have enough duration for it to have a long term conclusion. And for lastly, the fifth, there are no limitations as well. So, are these experiments successful? Some of these experiments shows minor changes, some shows dramatic changes. For example, in the equatorial Pacific, there are small changes in chlorophyll concentrations in iron X1, whereas there's dramatic changes in biogeochemical responses. And then there's also a taxonomic shift toward diatom-dominated phytoplankton communities. And then in the Southern Ocean, some of the experiment also results in diatom-dominated bloom. And then there's also a few other experiments that results in no shift to diatom dominated community and no detection of fertilization induced export. And looking at the experiments done in subarctic North Pacific, since one exhibits a shift from oceanic diatom to rapidly growing neritic ones and has the greatest changes in biogeochemical parameters. There are no detection of large carbon export flux in SITS 1 though. And lastly is the subtropical North Atlantic. So the end results, it shows an increase in phytoplankton abundance. Potential future for ocean iron fertilization. The main few things that need to be considered is the location, the timing, the duration, strategy, effectiveness, and side effect. I have prepared a poster to show. Is my poster on ways to improve iron fertilization. On the left, you can see John Martins's picture, the person who hypothesized about ocean iron fertilization. And the first thing to consider is the location. Where is it? Where is it most suitable? We have to choose places with a high silicate concentration and low grazing pressure, and also an appropriate eddy center for an ideal conditions of low current and high vertical coherence for easy identification and tracking. The next one, it is timing. For this experiment, it is have to be done during summertime, during the hot weather, for maximum light availability. So for the Southern Ocean region, December to early January is the most optimum due to an increase in nutrient flux from subsurface waters. Next is the duration. More than 40 days is sufficient to cover the full influence and response time from the onset on to the termination. The length of these experiments also must be in consideration with the amount of money that we use and the effectiveness. Also, the post-assessment is required for effectiveness. And then moving on to the strategy, use the appropriate iron addition, in this case acidified iron sulfate, which are bioavailable and cost friendly. The next strategy is fertilize a large area that will reduce the dilution effect with unfertilized water on the surface. And then, of course, the last one is multiple iron infusions at intervals at around 10 to 15 days, and also an interval of 1 kilometer each time. And then moving on to the effectiveness, tracing of fertilized patch by the Argos equipped drifting buoys that is released beforehand. And lastly, of course, there will be concerns about this ocean iron fertilization, right? So we must also consider the side effects. The possible side effects after an experiment can be continuously monitored from optical sensor equipped autonomous mode profilers and autonomous benthic vehicles like crawlers that can perform long-term benthic oxygen measurements for a long time.
That's it from me. Thank you for watching.